Um, are you muted, Candace?
Can anyone hear her?
I can't hear her at all.
Okay.
How about now? Can you hear me now?
There you go. Hi.
Ah, there we go. Hello. I've just been talking to myself.
Hello.
Okay. So, start that all over again. So you guys are scheduled to have a test this Sunday. That's chapters, I believe 7, 8, and 9. We're almost through 8, and 9's not too long, but I'm not going to force us to get through that stuff today. So your test will actually be moved to the following Sunday. Okay. So if you want to make a note somewhere, and I will change, I'll put a little note on the test, but it'll be in 1 week. Now we're not going to just lecture on this stuff all next week. We will lecture through information on the test. I'm just going to push the test back a week. So yeah, so let's get started. Let's see. Anybody been keeping up with the election? Somebody will
Nothing
put that.
changes, nothing to keep up with.
Yeah, right. I know. It's like snail's pace. Hopefully they can put us all out of our misery sometime today or tomorrow. All right, let's do some chemistry here. So we left off, we were talking about Lewis dot structures. And so we had just looked at expanded octets. And so the ones that like to have expanded octets again are anything like phosphorus, sulfur, chlorine, or anything bigger than that is going to possibly have an expanded octet. So looking at this Lewis dot structure here, we've got this thing called PO4 - 3. And there are two different structures. Because phosphorus is one of those things that can take a expanded octet, we could make our structure like this, or we could actually make it like this, because phosphorus can have 10 in its valence. So how would you know? I wouldn't expect you to be able to draw two different ones of these, all right? But I could give you each of these and ask you which one is more stable. And in order to determine which one of these is more stable, we need to talk about this thing called formal charge. So each of the atoms within a molecule is going to get a formal charge. And you can think of formal charge as like the distribution of electrons, or how much negative or positive charge is sitting around that atom. And this is the formula for formal charge. You're going to take whatever atom you're looking at. So each atom will have its own number formal charge. Okay, it's not one for the molecule, it's one for each atom within the molecule. So you'll take the valence electrons. So for instance, phosphorus is in column 5. So its valence electron number is going to be 5. Okay, so for this one here, formal charge is going to equal my valence, which is 5, minus my number of bonds minus my number of lone electrons. Or kind of an easier way to think of that is valence electrons minus lines minus dots. So phosphorus in this situation, we said it has 5, and then we're going to subtract the lines. So it has 1, 2, 3, 4 lines. So minus 4 lines. Does it have any dots on the central atom? No, in this case, we don't have any dots. I know there are dots on the oxygens, but we're only going to include what's surrounding that atom. So we don't have any dots. So formal charge here is going to be 5 minus 4, or it's going to equal 1 or plus 1. So that's where that plus 1 is coming from, okay? And that plus 1 is talking about the phosphorus. Now, all of these oxygens have a symmetrical setup. So if we're going to calculate the formal charge, let's say of this oxygen here, first we go with the number of valence electrons that oxygen brings. It's in column 6. So we're going to say 6 minus, first we subtract the lines. So there's one line. Then we're going to subtract all the dots. 1, 2, 3, 4, 5, 6. 6 dots. So it's going to be 6 minus 1 minus 6, or negative 1. All right, so that's where this negative 1 is coming from. So you can kind of think of it as like the electrons are hanging around here more at a negative 1. Here, they're kind of not hanging around. They're giving this an overall positive charge. Now, with formal charges, the formal charges of each atom needs to add up to what the overall charge is on the molecule. So if the overall charge is 0, your negatives need to equal your positives. In this case, the overall charge is a negative 3. So I've got plus 1, and then I've got negative 1, negative 2, negative 3, negative 4. So plus 1 and a negative 4 gives me the negative 3. So you always want to make sure that your formal charges add up to whatever that charge is. And again, you may not have a charge. It may just be charge neutral or 0. So that's what's happening with all these numbers here. Now, why? Now we've got this other structure, and we want to calculate the formal charge for these. So again, I wouldn't expect you to come up with each of these, but if I gave these two to you, and obviously you wouldn't have the formal charges on there, you would tell me which one's more stable. Well, looking at this one, if we happen to make a double bond on one of these oxygens, it changes the formal charge of phosphorus to 0, right? Because if I look at phosphorus again, it's 5. I subtract lines, 1, 2, 3, 4, 5, okay? And then I don't have any dots. So the formal charge on the center one here is 0. This oxygen over here has a valence of 6. We subtract lines. So 2 lines connected to that oxygen. And then we've got 4 dots for a total of 0. So 0 here and 0 here. 0 is much more stable than a plus 1. So whenever you can make zeros, especially a 0 on that central atom, that's going to create stability, okay? So 0 formal charge is more stable. If we can't have 0, if your option is between like plus 3 and plus 2, go with the lowest number, or the number that's closest to 0. So if it was minus 3 and minus 2, it would be minus 2. Whatever's going to hug 0 is what you want to go for. And then your negative charge, or your negative formal charge, is always going to be located on the most strongly electronegative atom. Now, what does electronegativity mean? We talked about that. That's an atom's sort of desire or greediness for electrons. So if something is electronegative, it means that they're going to hold the electrons closer to them. So these negative charges here in the oxygen, we've got a negative there, there, and there. This one's neutral. These have a higher electronegativity, and they also have a negative formal charge. So you can sort of equate those two numbers to each other. Negative formal charge, strong electronegativity. So I want you to do a Lewis dot structure for sulfate, SO4 2 minus. And I want you to tell me what the formal charge is on each of the atoms within it. All right, so first do a Lewis dot structure, then give me the formal charges. And I'll give you, it's 12:42, I'll give you 5 minutes for that one. If you have any questions, just ask. All right, so we're looking at SO4 with a 2- charge. This is also known as sulfate. So the first thing we want to do is add up how many valence electrons we get to mess around with. So sulfur is going to bring 6 to the table. Each oxygen brings 6, and we have a total of 4. And then this 2 here, it's a 2-, which means we have an additional 2 electrons. So I'm going to add 2, right? Because what we're counting here are the number of negatively charged electrons. So a negative value will create an addition. This means we have a complete 32 electrons. So when I'm drawing this, I'm going to put sulfur in the center, oxygens on the sides, and then I'm going to stick it together with a single bond. We're going to go ahead and or not double up. We're going to fill the outer guys first. So each oxygen is going to need 6 more. That is in fact 32 electrons, and everybody's happy. Sulfur is happy with the 4 bonds. So I'm going to put a charge around it. Now for calculating formal charge on each of these, sulfur has, so formal charge for sulfur is going to be, where are you, sulfur? 6, because it's in column 6, minus your lines, so 1, 2, 3, 4, minus your dots. We don't have any dots. So this is going to equal a positive 2. Let's find the formal charge of oxygen. Oxygen is usually pretty greedy with electrons. Oxygen is 6 because it's also in column 6. And then let's count it up. So lines, we have 1 line. Then we have 6 dots. So I'm going to subtract 6. This means that my overall formal charge for each of these oxygens is -1. I'm going to put a little +2 next to it. Sometimes that's how you'll see it written. And then each of these oxygens has a formal charge of -1. One way you can check, one way you can check and see if you did these right was add the charges up and make sure that they equal, add up your formal charges and make sure they equal the total charge. So in this case, we have a +2, and with all of those negatives, we have a -4. So we end up with a -2. So we have in fact done the correct formal charge. Okay. So another thing that I want to look at is resonance structures. So this here, these are not resonance structures. These are 2 separate structures. And we were just trying to decide which one was in fact more stable. They're not both existing simultaneously. There's just one that's like better than the other one. And we, because of formal charges, we think with that 0, that's going to make that a more stable structure. So we like this one for stability. This one just isn't really happening. There's another thing though with Lewis dot structures called resonance structure. And a resonance structure is when you can draw a Lewis dot structure in a couple different ways and they're all correct. So I'll show you with carbonate here. And I'll tell you, let you know how you know it's a resonance structure, like what point you get to that you're like, yep, this is definitely resonance. So we have CO3 with a 2- charge. Carbon is going to bring 4. Each oxygen brings 6, and there's 3 of them, and then we add the 2- charge. So I have a total number of electrons. I'm writing my Lewis dot structure for this. I have a total electrons of what, 18, 19, 20, 24. So I'm going to put carbon in the center. I'm going to stick it to my 3 oxygens. And I'm going to start making the outer guys happy. So add 6 to each of these. Okay, so 24 electrons are on the board right now. Are the oxygens happy? Yes. Is the carbon happy? No, it's close to it, but it's not quite there. So what we have to do is make a double bond. Now you get to this place where you ask yourself, which oxygen should I do the double bond off of? If I count this as oxygen 1, this is oxygen 2, and this is oxygen 3, where could I put that double bond? Well, I can put it on any single one of them. So I could choose oxygen 1 and put my double bond right there. Or, and then, get rid of those electrons here. Get rid of these. So that'd be a correct structure. I could also have, instead of putting the double bond there on oxygen 2, I could have put the double bond here. Could I have done it on the 3? Yeah, I could have done it on the 3 as well. So all of those are correct structures. So sometimes you'll see these resonance structures drawn like this, carbon, make it symmetrical, oxygen. Get rid of this one. So it'll have this sort of intermittent arrow, and it'll draw each of the possible options. So I'll do another one here. Carbon, single, double, double, single, oxygens. So all of these structures are correct. And in fact, they're sort of all simultaneously happening. Like that's why they're called resonant. They're resonating between each of these possible options. You could almost think of it as like this double bond is sort of oscillating around, where each bond has like a net bond of 1 1/3 length. So anytime you come to a place where you can, in fact, make a double bond, but it doesn't matter which oxygen you put it off of, we're going to classify that as a resonance structure. And if you're thinking, well, couldn't I just put the double bond on all of them at the same? So I'll draw this in red over here because it's incorrect. So if we were to get rid of this and put another bond here and get rid of this and put another bond there, you're saying, oh, well, we'll just make a double bond on all of it. Well, what's happening with carbon? It has access to 2, 4, 6, 8, 10, 12. Carbon does not want access to 12. It definitely doesn't have an expanded octet. Okay, so you got to pick one of the oxygens to be your double bond. Questions on resonance structures? You'll know that you've hit a resonance structure when you get to that point where you need to make a double bond. And it's like, do I want to put it here? I could put it here. I could put it here. All right. So let's keep going here. O3 is another example of a resonance structure, but I'm not going to go over that one. I don't really like that one a whole lot. Okay, so the last thing we're going to look at is the covalent bond strength. So how strong is the bond between two adjacent atoms that are sharing electrons? And we've gone over this a little bit. You know that single bonds are weaker than double bonds, and double bonds are, or single bonds are, rather, let me say them the other way. Double bonds are stronger than single bonds, and triple bonds are stronger than double bonds, right? Your single bond is going to be like having one stick and breaking it. Your triple bond is going to be stacking 3 sticks together and trying to break those. And so when we look at this word bond enthalpy, and hopefully that word enthalpy is somewhat familiar for you from our previous chapter with thermochemistry, we can write this as delta H. And so bond enthalpy is going to be the energy stored in different types of bonds. And there's no, there's not going to be any equation for you to calculate bond enthalpy. That would be something that I'd give you, all right? Or you'd pull off of an appendix. That is experimentally calculated. So your bond enthalpy is always going to be positive, because when you break a bond, it's an endothermic reaction. So breaking bonds is endothermic. If breaking bonds is endothermic, then fusing something together would be exothermic. So let's look at a chart that has a bunch of these values. All right, so here's a table, and this is in, it's not written on here, but this is in kilojoules per mole. So what we can see is all the different types of bonds that are happening, and these are all covalent bonds, so we're not having any sort of metal, non-metal ionic stuff here. And if I was to break a carbon hydrogen, it would need 413 kilojoules per mole of energy. Multiple bonds down here, we can see that as we move into double bonds, we're going to need more energy. And so we can use this chart or use these numbers. Yes, David, yes, kilojoules per mole will be the unit that you use for your bond enthalpy. Because we're not going to talk about we don't want to talk about the amount of energy that would be for one single bond breaking or coming together. We want to talk about it on like a human scale. So that's why it's per mole. So we can use bond enthalpy actually to calculate our delta H of reaction. So we were calculating delta H of reaction before, products minus reactants. It's kind of a similar thing, but we're going to be looking at bond enthalpies. So the way that you're going to work this is you're going to sum up the bond enthalpies of all the things that are broken, and you're going to subtract them from the bond enthalpies of all the things that formed. So all the broken stuff minus all the formed stuff. And make a little note up here that this is sort of like our reactants side, and this is our product side. So let's look at an example here. And do note that this is a molar relationship, or it's stoichiometrically related. So if you happen to have a 2 or a 3 or some other coefficient, you would need to multiply your values by that. So you'd want to put that out in the front. But if we're looking at this here, we've got CH4 plus Cl2, and it forms CH3Cl plus HCl. So it might help you to draw the structures of what you're starting with. So I've got CH4, so that's going to look like this. It's methane. Oh, come on, H. Plus our Cl2. So you've got to actually draw the structure. So we've got Cl and it's bonded to itself. I'm going to put some lone pairs around there. And then we end up forming CH3Cl. Carbon likes to go in the center. The H's are going to be on the side. And we've got a Cl plus HCl, which is going to be H combined with a Cl. And there are some things going on around here as well. So our delta H is going to equal all the bonds that need to be broken. So I just look at all the bonds that I have to tear up on the reactant side. Sometimes people will say, oh, but I'm forming some here and I'm subtracting some here. So then I would only really net a missing one, or getting rid of one or breaking one. I just add them all up. I think it's easier. So on this side, I have how many hydrogens? I have 1, 2, or rather these hydrogen carbon bonds. I've got 1, 2, 3, 4. 4 hydrogen carbon bonds that I have to rip apart. So I'm going to write the number 4 because there's 4 of them. Let's put a parenthesis around this. And then I need to figure out what the energy is that I need to break that. So we go up to our chart and we have a single bond between carbon and hydrogen. So our single bond between carbon and hydrogen is 413. So 413 plus, I have one chlorine-chlorine bond that I'm gonna break. Okay, so let's go up here and check out, where's our chlorine? There's our chlorine-chlorine, 242. And just one of those. So 1 times the 242. You don't have to put the 1 in, but I'll just do it so that you know we only have 1 there. All right, so this is all of our reactant stuff. So we've torn everything apart. Now we're gonna fuse it back together in a new way. So I'm gonna subtract all the formation stuff. Why am I subtracting the formation stuff? Because it releases energy when you form the bonds. So you don't need to put a negative in front of this. You can just use that negative in front of the whole thing. So we'll use our positive values. In this case, I've got 1, 2, 3 hydrogens. So 3 times the hydrogen bond formation, which is the same thing that's over here, 4, 1, 3. Plus I have a carbon and a chlorine bond. So I'm gonna look up carbon and chlorine right here, 328. How many of those am I creating? Just one. So 1 times the 348. 328. And then the final thing I'm going to make over here is a hydrogen chlorine bond. So I'll reference hydrogen chlorine right here, 431. And there's just one of those, 431. So we're going to tear it up and then we're going to put it back together in a new way. Now, it is important to know this negative talks about this entire thing here. So we want to make sure that we are summing this together first and then subtracting it as a whole. You don't want to add these and then just subtract the first thing. You want to subtract each of those values. So when I plug this into my calculator, this first value here becomes 100 or 1,894. I'm sorry, that looks like a negative and it is not supposed to be a negative. The next one, so we're going to subtract 1,998. So that's what this value is here. And you should end up with negative 104. And the units on this are kilojoules, or kilojoules per mole. This is exothermic. Okay, because we have a negative value. So if I run through this chemical equation or this chemical reaction, I will actually produce heat. And you can figure that out from those values on the chart.
So the products, are they a negative value to begin with?
Over here,
No, on the left side.
on this side, these are positives.
Reactants.
Reactants. Yeah, so all of these values are going to be positive. Okay, so just leave them positive here and leave them positive here. The negative will take care of that, like forming and breaking.
Gotcha. I think I was confused by the delta H equal sign, like kind of touching the parentheses. I thought it was a negative.
Oh, okay, sorry. Yeah, no. So keep them all positive because all the values here are positive. Any questions on that? You're just going to break it up and then you're going to put it back together.
Where did you come up with at the end of the equation 4 minus or H minus Cl?
Where did I come up with that? It's H bonded to Cl. Yeah, so it's this thing here.
Gotcha. I didn't write that part down.
No worries. Yeah, so all I did was take the equation or the reaction and I just drew it into Lewis dot structures. Because you know, if you get better at these, you could look at this and say, oh, that's going to be 4 hydrogens bonded to 1 carbon with a single bond. But I would lay them out like this. because then you can really visualize how many bonds there are that you need to subtract and add. All right, we are going to move into the next chapter, which is tied in a lot with chapter 8. Some classes will actually teach these as one giant chapter. But our text separates it up for us.
I just ask a quick,
Yeah, what's up?
what if you had a double bond on those? And would it, you're counting an extra bond, but then the
If you have a-
number's still the same in the chart, right?
No. If you did have a double bond, you would use one of these values here.
Okay, all right,
That's a
sorry.
good
yeah.
thing to know. Yeah. So let's say we had a carbon-carbon double bond. I don't count that as 2 single bonds. I count it as 1 double bond.
Okay.
Okay. All right, so the next part here is called VSEPR model or VSEPR theory. So we have our Lewis dot structures, and then what the Lewis dot structures are limited in that they are on a flat piece of paper. So what we want to start doing is taking these Lewis dot structures and sort of expanding them into 3-dimensional space. A lot of times we do this in class with like ball and stick models, or you can use like toothpicks and marshmallows to get this visualization 3-dimensionally. But in these slides here, they do have some of the pictures sort of trying to draw them out in 3-dimensional space. So VSEPR stands for valence shell electron repulsion theory or model. And what this states is that an electron or a group of electrons, or a lot of times they refer to them as domains of electrons, want to get as far away from each other as they possibly can because they all have negative charges. So an electron domain is, so we're going to say an electron domain. One electron domain is equal to a single bond, it could be a double bond, could be a triple bond, or it could be a lone pair of electrons. So going back over to what we had here, if I was looking at this structure and I wanted to say, oh, how many electron domains are there? You're only going to look at what's happening on the central atom because that is the only thing that determines its shape. Electrons that are on the outer atoms, those don't repel each other to create a 3-dimensional shape. So here, I would say that this is 1 electron domain, this is 2 electron domains, and this is 3 electron domains. So this would have 3 domains, or 3 areas of negativity that want to spread away from each other. Why do we consider a double bond 1 domain? Well, the double bond is a unit. It's sort of fused together, right? It's attached on the carbon end, it's attached on the oxygen end. So we've kind of pinched the edges. So we consider that 1 domain. Same thing is true if we're talking about a triple bond. You're going to group that as 1 domain. If I do the structure for water, so we've got H2O, There are 8 electrons to play around with. It looks like this. H. H. If I was counting electron domains, I would say that there is 1, 2, and then each lone pair counts as 1, 3, and 4. Okay, this has 4 domains. We don't count the electrons by themselves, and we don't count them as one giant clump. They have to be a paired set. But notice these are on the central atom. These guys over here are not on the central atom, so I don't involve them. Okay. So hopefully we're good with domains. Now let's see how we would classify each of these domains. So this I would count or call a bonding pair or a bonding domain, because it's a domain that includes a connection or a bridge. These are a lone domain, or they are an area of negative electrical charge on the central atom, but they don't have a partner. So we want to be able to separate these out into bonding domains and lone pair domains. So water, for instance, has 2 bonding domains, 2 bonding domains, and it also has 2 lone pair or lone pair domains. Sulfur up here, or sorry, not sulfur, carbonate has 3 bonding domains. Each one of those is involved in some sort of bonding situation. So we're going to say 3 bonding domains. And this all comes into play on how the things are shaped. So we want to look at this VSEPR formula. And we're going to classify everything kind of based off or using this formula. So the A, it's consistent for all. The A stands for atom. It just means your central atom, right? So you don't write it in as, like, if we're looking at CO2, we wouldn't write the A as C. You would just write it as A. When you're writing your VSEPR formula, just start off with the letter A. Then you're going to write the letter X. And X is specifically talking about bonding domains. Okay, so you'll put a little subscript to tell yourself how many bonding domains you have. If you have any lone pairs on the central atom, those lone pairs will be denoted with an E. And again, you put a subscript to tell yourself tell the reader how many of these lone pair sets do you have. So if I'm looking back over here at our 2 examples, for carbonate, I have 3 bonding domains. So if I'm going to write the VSEPR formula, valence electron shell repulsion formula, I'm going to write the letter A always. And then I'm going to write X. X is talking about bonding domains. So here I have 1, 2, 3 bonding domains. Do I have any lone pairs on the central atom? I don't, so I don't need to include an E. And so when you see something that says AX3, that means 3 bonding pairs around the central atom. Versus water. Water has 2 bonding pairs, but it also has 2 lone pairs. So when I write this formula, I'm going to write A. X is my bonding pairs. I have 2 of those. So AX2. Lone pairs are going to be represented with an E, and I also have 2 of them. So the formula for this is AX2E2. So I'm going to give you, I want you to do the Lewis dot structure for NH3, and I want you to tell me what its formula is as well. You can't, I mean, if you're really good at these, you can do them in your head, but I would just write the Lewis dot structure out and then give me the correct formula for it. Okay, so NH3, to do the Lewis dot structure, you have to figure out how many electrons. You have 8 electrons to mess around with here. The N is going to go in the center. H, 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 bond, bond, bond. I have 2 more electrons. I'm going to put them right here on the central atom. Hydrogens are happy because they like duets. Nitrogen is happy because he has access to 8. So this is a correct drawing. If you had put your 2 dots over here or your 2 dots down here, that's fine because it's a 3-dimensional structure. So I can kind of rotate it around in space. But it does need to be on the central atom. So when I'm writing the formula, I'm going to put my A. X is going to include all of the bonding pairs. So here I've got 1, 2, 3 bonding pairs. So that's where the 3 is coming from. And then I have 1 lone pair on the central atom. So I do need to add an E, and there's an inferred 1 there. Okay, you don't need to put the 1 in.
Could we have laid it out so there were like an H on each side, on 3 different sides, and then 2 dots on one side, or is that wrong?
So you're saying, so I'm going to put the N in the center. You put the H where on top?
And then like side, then bottom, and then 2 dots on the other side.
Like this? This and this are the exact same thing. It's just been rotated in space. So we still have 3 of these and 2 of those. And you've got to think that this thing is popping forward and back in space. Okay, so it's not actually making like a flat square. It's making a tetrahedral shape or a little pyramid. So if you were to take like a marshmallow and put 4 evenly spaced sticks and then 4 little marshmallows on the outside, you make a little pyramid.
Could you explain formal charge on this particular?
For this one?
Yep, please.
Yeah, let's do it. Okay. So formal charge, let's do it for nitrogen. So nitrogen, formal charge, it's in row 5. So we've got 5 minus 1, 2, 3, 3 lines, and then 2 dots. So the formal charge is going to be 0 on nitrogen. Hydrogen, and this is for nitrogen, okay. Hydrogen's formal charge, we're in column 1, and we just have a line, -1, so 0. So these also have a formal charge of 0. So this guy's very stable.
Right, so, yeah, I think what I was trying to do it in my head, and I think because I subtracted the lines for nitrogen, I forgot that I also do it for hydrogen.
Mhm. Yeah, yeah. Yeah, the line is being shared between both of them. So they both have to take it into account. So why do we care about these silly little equations and what are they telling us? Well, they are really good to use against this chart, which you'll want to have access to. Just have it available when you take your next test. This chart right here. And usually I have my students memorize all these shapes, but you'll get to have it. So Merry Christmas. All right, so if we have a situation like CO2, CO2 is going to have a linear structure, and let me show you. So it has a formula of AX2. You get out of there. So I'll just real quick draw CO2. We've got carbon in the center, oxygen's on the side, single, single, make the outer guys, oh, I have 16 electrons to play around with here, right? So 4, 12, yeah, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 16 electrons on the board, and this is gonna share, we'll make this a double bond, and this is also gonna share. So when writing a formula for this, I figure out how many electron domains I have. One here and one here. Neither of them are lone pairs. They are simply two just bonded pairs. So I'm going to write AX2. The X, remember, is talking about one single, one double, or one triple. All right, so I have, in this case, I have 2 double bonds. So I wouldn't count that as 4. So when you have 2 domains like this, there's a couple things you can do. One is just to go back and reference the chart. Okay, if I have that, that means I have a molecular geometry of linear and I have an overall geometry of linear. Molecular geometry is telling you the position of atoms. Overall geometry is telling you where the electron groups are. Or electron domains are. So overall geometry takes into account all electron groups. Molecular geometry takes into account where the electron groups are that are attached to the atoms. This is a good rule of thumb. If you don't have any lone pairs of electrons on the central atom, you only have bonding pairs, your overall geometry and your molecular geometry will be the same. So if you see here, there's no E here, same. No E here, same. No E here, same. They start to change. Your overall geometry will become something different from molecular when we start adding those lone pairs. So the shape for carbonate is, for carbon monoxide, or no, CO2, we're doing carbon dioxide. This is going to have a linear structure. You can reference the chart, or if you want to think about it like a tug of war. So if I had, if I wanted to create something symmetrical, oh no. Whoa, I don't want you. We're just leaving the circles. But if I want to create something symmetrical, because these electron groups kind of want to get as far away from each other as they can, or you can think of it as like 2 people that just really don't like each other, right? Or it's really, really hot and sweaty and everyone's super smelly and you're trying to get in 3-dimensional space away from each other. So in this case, the farthest that these 2 groups can get away from each other is 180 degrees. So the bond angle here is 180 degrees, and it's sort of like a tug of war, two people pulling in opposite directions. So this formula will always give you something that's linear. And that is linear for the electrons. So the electrons themselves are 180 degrees from each other, and the atoms are also in a structure 180 degrees from each other. Let's look at one that's a little bit more complicated. No, I don't want to open test generator. So if we do BF4, or sorry, BF3. So this is our linear guy. BF3, I have a total of 24 electrons to play around with. B is going to go in the center, F's on the side. Bond it, and then put my electrons, fill the outer guys and fill the inner guys. Oops, stick it together, sorry. So there's 24 electrons. Remember, boron is one of those that is okay with just having 6. So I don't need to force a double bond here. So when looking at all the electron groups, I've got 1, 2, 3, and they're all bonded, right? They're all attached to an atom. So this is going to have a formula of AX3. There's no E. What is this shape making? Well, this angle here is creating something that's 120 degrees, and we call this trigonal planar. It's like a pizza cut into 3 slices, right? If there were 3 people and everybody wanted the exact same amount of pizza, you would give each person a slice that's 120 degrees. Can these things get any farther away from each other than that? No, they can't. Because the electron groups are 120 and each electron group is attached to an atom, the atoms are also 120 degrees. So both the molecular and the electron geometry is this trigonal planar. Now let's look at SO2. This is where it gets a little bit more complicated. SO2, we have 18 electrons. I'm going to put sulfur in the center, 2 oxygens on the side, bond, bond, make the oxygen happy. I end up having 2 more electrons, and then I've got a double bond to sulfur. So I'll do it on this one. Could I have done it on the other oxygen instead of this oxygen? Yes, that makes this actually, in fact, a resonance structure as well. So when I'm writing my formula, I have 1 atom in the center. I have 2 domains that are bonded. So X is going to be 2. And then I have 1 lone pair right here, AX2E. Now the overall geometry, and again, all this is summarized on that sheet, but the overall geometry is looking at all the electron groups. So in this case, I have 1, 2, 3 electron groups. All right, so overall geometry will be trigonal planar. Because 3 electron groups are going to make the pizza with 3 slices. My molecular geometry is different though. What I want to do with my molecular geometry is almost ignore what's happening here and just look at the shape of the remaining atoms. So the way that I have it drawn, it makes it look like it's linear, but it's not actually linear. Think about your pizza. So if we have a pizza and we break it into 3 slices, okay, and I ignore this, what is happening with that final length? It's forming a shape that is bent. So the molecular geometry on this is actually bent. The lone pair of electrons here is pushing those other 2 groups down. So without this lone pair, yeah, this would be linear, but with that lone pair, it's now shoving those down into this bent shape. So that's where this idea of a difference between overall and molecular. Sometimes bent is also referred to as V-shaped. You can see it here, V-shaped. So let's keep moving on with the shapes. We'll do CH4. CH4. This is methane. You have 8 electrons to mess around with. Hydrogen, hydrogen, hydrogen. Okay. And the structure is done. So if I'm going to write its formula, I'm going to write A, X, how many groups do I have? 1, 2, 3, 4 groups. Do I have any bondeds here, bonding pairs here? No, I don't have any bonding pairs. Okay, so there's no E. When there's no E, I know my overall and molecular are the same. Now, what is that geometry? If it really looked like this in real space, we would call it like square planar, but it isn't actually flat. Because here, drawn like this, the distance between these adjacent electron groups would be 90 degrees, right? But that's not as far as they can get away, or as far as they can get from each other, because we can actually pull the structure forward and back in space. So this guy here is, think of this one as sort of coming forward in space towards you. Come on. And this one is sort of moving back in space. So one is coming out towards you, one's going back, or you have, and then you have 2 parallel. Let me give you, because these drawings can be hard to visualize. I haven't done a lot of chemistry, but like this here. Okay, so 3 little guys that are pointing down and 1 guy pointing up, or a little pyramid. This shape is known as a tetrahedral shape. Since there are no lone pairs, they're all bonded. The electron groups are tetrahedral, and the atoms themselves are also forming a tetrahedral shape. We'll call this one tetrahedral. Tetra meaning 4. Let's do, to build onto this, let's do PH3. So PH3 has 8 electrons to mess around with. We'll have P, H, 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 and then I have a lone pair of electrons on the very top. So there's a lone pair. That means I've got A, X, my X is 3, and my E will be 1. Anytime you have an E, molecular and overall are going to differ. The overall geometry lets you know how many electron groups you have. So I have 1, 2, 3, and 4. So I'm making a tetrahedral with the electrons. So this is tetrahedral. But my molecular geometry is saying, well, what are the atoms themselves doing? How do the atoms look? So if I've got a tetrahedral shape, think about having your pyramid shape and you sort of ignore the top. What you have left are these 3 prongs pointing down. That shape where you have 3 prongs pointing down is known as trigonal pyramidal, because you're making a little pyramid. My drawing is garbage over here. So let me try and pull up one of these that gives you a little bit of a better structure for that. Yeah, so this right here is a trigonal pyramidal. The 3 outer atoms are pointing down, and then the top space, there are electrons there, and they're sort of pushing the other ones down. Don't confuse trigonal planar with trigonal pyramidal. Trigonal planar is my flat pizza. Trigonal pyramidal is when they point down in the prongs. So all of these have 4 electron groups. This first one where it's tetrahedral, it doesn't have any non-bonded pairs or lone pairs. This next one, trigonal pyramidal, it'll have 3 bonding and 1 non-bonding. Let's see what happens when we get 2 and 2. So that's going to be our structure like water. So water. H2O. 8 electrons as well. Oxygen in the center, hydrogen, hydrogen, and then I've got 2 bonds here. So I do have lone pairs on my central atom. So I know for my formula, I'm going to have an A, I'm going to have an X, which is 2. I'm going to have an E, which is 2. Because each one of these pairs counts as 1 domain. So what is this shape? The electron, or the overall geometry, is saying, you know, take into account all electron groups, is 1, 2, 3, 4 groups. So this is tetrahedral. So the last 3 that we've grouped together, their overall geometry for each one of those is tetrahedral. But now what we want to do is take our tetrahedral, so think of it in your mind's eye, okay? You've got this little pyramid, 1 pointing up, 3 pointing down, and pop 2 of the ends off, all right? What you'll be left with is a structure that's called V-shaped or bent, all right? So we're going to say the molecular is V-shaped. Now don't be fooled, because sometimes water is drawn like this: oxygen, hydrogen, hydrogen, and maybe you'll put 2 dots on the top and 2 dots on the bottom. You say, well, it looks pretty linear to me. Well, these are sort of pointing up towards your face at a V shape. These are pushing against that. Let me give you a better drawing so you can see it right here. So take your original tetrahedral, rip off 2 ends, and what are you left with? This bent or V shape. Now again, normally I would have you all memorize all these shapes, but you are going to get access to the sheet while you're working on your exam. So just be able to reference this, okay? There are a couple more.
Where do we find this sheet?
It will be in the guided notes or in the notes on Moodle. Okay, it's also in your textbook. But if you go to your Moodle page and go to this chapter, chapter 9, and go to the notes / guided notes, it'll be right there for you, okay? So there are a couple shapes that go along with expanded octets. So if we have 5 groups on the central atom or 6 groups on the central atom, and we will get into those on Monday. Yeah, we'll get into those on Monday, and we'll do a little bit of practice, and then we'll move forward into the next chapter. But I will be, again, pushing your test off 1 week. So you do not have a test this Monday or Sunday, Monday. You'll find it on Moodle next Sunday, Monday. So we'll stop there. If y'all have any questions, hang around. Good luck, stay sane.